Y'all hear me okay?
Yes.
Thank you. So the good news about exponential function is you've seen it before, but I, a lot of people tell me that college algebra is a lot of repeat from your algebra 2, and that's true. I would love to say that we're going to be able to raise the level of what you've learned about exponential functions. Probably not, though. Most of this will still be pretty typical what you've had. But you've worked with the parent function already, even in this class. If y equals 3 to the x, that's an exponential function because your exponent on this base is the variable. And if you just do a simple table so you can plot, you would realize that when x is a negative 2, that becomes 3 to the negative 2, which means 1 over 3 squared, which is small, 1/9. So if I go to a negative 2, it's going to be very close to the x-axis. If I say let x equal to a negative 1, then 3 to the negative 1 really means 1 over 3 to the 1, which is 1/3. So it goes up a little bit, but not much. If I go to 0, if x is 0, 3 to the 0, anything to the 0 power is a 1. So I'm up here now. If I say x is a 1, then 3 to the 1 is a 3. If I say x is a 2, 3 to the 2 is a 9. So you got a 1 and a 9. So what's happening, 3 to the 1 is a 3, and 3 to the 2 is this is called an exponential growth. And as it goes to the left, it wants to get to the 0, but it never can because that's my horizontal asymptote. So we've already talked about this function in other contexts. And so that's today's lesson. And so that's my preview. In the lesson, we're going to talk about exponents and properties. I just did one of those properties. When I did the negative 1, knowing that meant 1 over 3, is a property of exponents. We're going to do a few more. Then, of course, we're going to be talking about exponential functions and graphing them. Then we're going to solve some equations that are exponential. And if we get lucky, we'll get down to the compound interest. And then we'll talk about continuous compounding. Okay. I thought we did some of this already, but I think we just did simple interest. I think we just did simple interest. 1 plus the interest rate raised to the number of years. I think we've done that. Okay, so let's go and try to fill in some of these gaps that are in the authors. And I was just realizing last period that I keep calling the author he, but the main author is actually Margaret Lial, and she's very famous when it comes to college algebra and pre-cal textbooks. So I should now start saying she. She's the one that wants us to do this. And this, I always hate filling in blanks because I don't always know what they want. I have one blank in here I still can't figure out. It's this one. So maybe somebody will tell me they can earn extra credit because I couldn't figure out what they wanted. If I just gave you a y equals 3 to the x, and I just gave you a whole bunch of answers when x was a negative 2, when x was a negative 1, when x was 0, when x was 2, and you notice this is what we're talking about. If y equals a to the x, so no matter what x I plug in, I always got a number out of it. Even this one up here, what if I say x is a 1/2? Then I have 3 to the 1/2 power. Well, that's another property of exponents. Anything to the 1/2 power really means the square root of that 3. So that's still a number. It's between it's between it's it's less than 2, but yeah, it is less than 2, but it's greater than 1. So it's greater than 1 because 1 times 1 is 1, 2 times 2 is 4, so I know it's between 1 and 2. So what I'm going to fill in the blank here is a to the x is a unique real number. No matter what x I use, I'll get a number out of it for all real numbers of x. We'll do these descriptions after I fill this side in, because I think this side is a really important side. A to the b equals a to the c. So we're looking at two functions with some mysterious variables. If this is true, this is only true if and only if, in this case, b was equal to c. This is only true if b equals to c. Or I can say this, if this is true, then this is also true, and go both ways. If this is true, then this is true. Or if this is true, then I know this is true. The exponents have to be the same. Now, in this one, if a is greater than 1, like I just used a 3, and now I'm going to talk about the two exponents, m and n. And m is smaller, less than n, then we know that a to the m has to be, did I have in the right order? I want, if a is greater than 1, I have them reversed, I think. No, I do want m less than n. And m is less than n, then a to the m is less than a to the n. Let's see if that's, oh yeah, because m is smaller. I was thinking m's bigger because it looks bigger than the n. That's silly of me. So if I'm going to give you an example. 3, I did 3 a minute ago. Let's take a small number, 3 to the 2. Let's compare it to a bigger number. That's big number on this side, 3 to the 3. Is this hold true? 3 squared is 9. Is it less than 3 cubed, which is 27? Yes. So as long as a is bigger than 1, the bigger the exponent, the bigger the number becomes. Okay? Now, if a changes, if a, we're not talking about being negative. We're never talking about negative a's. We're talking about a now becoming a number between 0 and 1, a fraction. If a is a fraction, that's what we're talking about, less than 1. So when I say fraction, 5/4 is a fraction. But that won't be true. That will be the same thing as letter C up here, because a is greater than 1. 5/4 is greater than 1. We're talking about fractions like 2/3, 1/2, 4/9. That's what we're talking about. And I'm going to say, and let m be less than n. Again, m less than n, m is less than n. Then he's saying that, she's saying, that a to the m now is not less than, where is it? Not less than, but greater than. It switches that symbol. Well, let's see if it works. Let me do a number that's between 0 and 1. Let me pick the 2/3, okay? 2/3 is now my base. Compare it to the second, and compare it to the third. I didn't even write the third. There's a third. M is less than n. Let's see. 2/3 squared is 2/3 times 2/3. That's 4/9. That's less than half. That's almost a half. Let's do 2/3. That's 2/3 times 2/3 times 2/3. That's 8/9. No, that's 8/27. That is smaller than 4/9, because 4/9 is almost a half. 8/27 is not even a third. Not even a third. So it's smaller. So notice what happened? The larger the exponent on a fraction gives you a smaller number. Because every time you multiply by a smaller number, the answer gets smaller. These are important things to think about. I don't know if you'll apply them to these graphs, but all right, you're gonna have to help me out here. Because the descriptions, I'm not sure what she's thinking all the time. Uh, y equals a to the x can be considered a function f of x. Well, that to me, I think what they're saying, she's saying, is that if y equals a to the x, then f of x is a to the x because it's a function called a to the x. A can be a lot of different numbers. And with the domain, well, I just showed you a picture of one of them up here. The domain is all possible x's. And as it goes to the left forever and ever, it's all possible x's all the way to negative infinity. It never crosses the x-axis, though. It tries. And as it goes to the right, he's constantly increasing. But whether you think so or not, it is going up and over, up and over, up and over, up and over, up and over. So as you get farther in the x's, you are still going to be finding them. So I'm going to say that the domain is negative infinity to infinity. All the time. All the time. That's for any exponential growth. And I didn't mention to you that other one with the fraction, y equals 2/3 to the x. What happens here is it became the other way around. It decayed. But it has the same domain. It just changed which way it's going. Okay? Next example. 2 to the 3 is less than 2 to the 4. 2 times 2 times 2 is 8. Is that true? Is 2 to the 3 less than 2 to the 4? Yeah, that was 16. That was 8. That's 16. For all a greater than 1. So what we're talking about is that first picture I drew. Okay? As I went from if I go from this way, the function is constantly getting, even right here, you don't see it because it's going up very slow, very slow, very slow, but eventually it starts climbing higher and higher and higher, okay? So what I'm going to say about that one, that if you increase the exponent, it leads to a larger number. And the function f of x equals 2 to the x is an increasing function. It's increasing as you go from the left to the right. It's increasing. Now, the next description was a is now between 0 and 1. And I showed you how that did this, remember? I showed you how that's going like that. Increasing the exponent means the numbers got smaller. Remember what we compared with? We compared 4/9 versus 8/27. They're getting smaller. So I'm going to say when you increase the exponent, it leads to a smaller number. Therefore, the function is a decreasing function. The function f of x is a of x is, anybody got a word for me I can put in there? Okay, I'm going to make up a word since none of you want extra credit. I'm going to say it's continuous. Why?
1 to 1.
Say it again. Oh, 1 to 1?
1 to 1. Yeah.
It is 1 to 1. I like yours too. I would have never have thought of using 1 to 1. But did you make that up yourself?
And no, I found it in the
You
book.
found, you found it in a book. Oh, the book. I'll still give you your points. What's your name? Oh, I can't.
Carla Martinez.
Carla. Yeah, Carla, you've helped me out before. Make sure you send me a message or I won't remember I said this to you. Okay. Thank you, Carla. Matter of fact, I'm going to give you double that I normally give because you actually read it in the book. Way to go, Carla. 1 to 1. That is true. I don't know why he wants to bring that up. I like my answer better, Carla. If its domain is from negative infinity to infinity, then it's continuous. But well, no, that doesn't mean it has to be continuous because it could be something could be continuous and it does this. That's continuous, but it breaks right here. So it's not. It still goes from negative infinity to infinity like this one did, but it has a break. So it's not continuous everywhere. You know what? Your answer has to be better. Is it 1 to 1? She says it is. Let's see. 1 to 1, the simple thing was a horizontal line test. Oh yeah, look at that. It is 1 to 1. How about the decay? How about the decay? Yeah, it's that one too. Okay, thank you, Carla. Oh, yay, Carla. Now I know what that answer is. I can sleep tonight. If a is greater than 0 and a does not equal to 1, then the exponential function with the base a is f of x equals a to the x. Why can't a equal to 1? Why not 1 to the second, 1 to the third, 1 to the fourth, 1 to the seventh? What's
The
wrong with
answer
those?
would be 1.
Huh? It's always 1. It's not increasing, is it? It's not increasing, nor is it decreasing. It's a constant function of a y is always equal to 1, horizontal. Nice job. Thank you. He wants us to talk about why we're restricting it to not be equal. And why does a have to be greater than 0? Interesting. What if a was negative? What if I was doing y equals a negative 3 to the x? Well, I'm going to show you. Simple table. Takes you 5 seconds to see something. What if x is a negative 2? That's a negative 3 times a negative 3. That's 9. What if x is a negative 1? That's a negative 3. That's just a, oh, that's negative. What if x is 0? Oh, that's okay. It's still a 1. What if x is 2? A negative 3. What did I just do here? A negative 3. Oh, I messed up here. These weren't right. That was for a 2, and that's for a 1. I should talk about, so I already have those answers. I have those 3 answers. What about, let me do x equals to a negative 2 like I had. That's a negative 3 to the negative 2. What does that give me? That gives me a negative, that's a whole negative 3 to the negative 2. That's a negative, that's 1 over a negative 3 squared. Because when you have a negative power, it goes downstairs. That's the same as 1/9, positive. What about a negative 3? Negative 3 cubed gives me, or it's negative 3, so negative 3 to the negative 3 means 1 over a negative 3 to the third power. Uh-oh, that's going to be negative because that's 1 over negative times the negative is still negative. Now it becomes a negative 1 over 3 times 3 times 3 over 27. Look what's happening. It's it's becoming positive, negative. Over here, look at, we had positive and a negative. We keep switching places, positive, negative. It doesn't work. It doesn't constantly give you increasing or constantly giving you decreasing. It gives you increase, down, down. It's very sporadic. Yeah, you can't have a negative power. I mean, you can't have a negative base, I mean. You can put the negative out front, but you can't make the whole thing negative. All right, let's plug in some function values. Let's see. f of x is 2 to the x, evaluate f of a negative 1. Well, that means 2 to the negative 1. That means 1 over 2 to the 1, which means 1/2. Just using your power of exponents, okay? How about if y is 2 to the x, 2 to the 3? Well, that's simple. That's 2 times 2 times 2. That's 8. All right, here's a hard one. 2 to the 5/2. I know what you're thinking. You'd rather use a calculator. You would rather say 2 to the 2.5 and use your calculator. But I don't want you to do that. I want you to do it like this. If you can do it by hand, try it. When you have this exponent rational, the 2 still gets the exponent of the 5, but this bottom here tells you what kind of root am I going to have. Square root. But we don't normally write the 2 there, but it is there, so it's the same thing as this, 2 to the 5, which means 2 times 2 times 2 times 2 times 2 square rooted, which means square root of 4, 8, 16, 32, which can simplify to square root of 16 times square root of 2, which can be 4 square roots of 2. There's the answer I would want. If you used a calculator, that's going to give you a decimal number that goes on forever and ever and ever and ever. And the only thing you're going to give me is an estimation. And I don't care what you give me for the estimation, I'm going to mark it wrong. Because estimate does not mean equals. Okay? It's an approximation. All right, now, I give up on letter D. I cannot do this by hand. If I'm doing 2 to the 4.92, the best I can do in my head, guys, is say it's approximately 2 to the 5, which we just did it over here a minute ago. It's close to 32, but it's not exactly 32 because I'm missing some part in the exponent. So if you could please, and before I ask someone to use a calculator while we wait for someone to key that in, make sure you sign in and chat. If you do not sign in and chat, and I only have 12 of you that have, that's going to be an awful lot of people I'm marking absent because I will not know you're here. I don't see any pictures. All I see is my iPad because I started right away. Yep, there you go. See, you didn't read your announcements. And I told you guys to sign in. All right. Did anybody do this approximation of 2 to the 4.92 and give me a rough idea what it might be?
It's
At least
30.27.
You can go, it's fine.
you go to 28?
No, it's a 3 after that.
Oh, what was she saying? Who was talking?
Oh, I was Sir Jillian.
What were you going to say, Julian?
Oh, I was gonna give you the same number.
Oh, thank you very, very much. So 30.20, hey, that is so odd to have two people going to talk at the same time. Whew, I'm going to have a good day today. So this isn't exactly 32, is it? Because my 32 was an approximation. I didn't think I was going to be that far off because it's 0.92. It's only 0.08 away. But that makes a big difference when you talk about exponential functions. 2 to the 4.92 and 2 to the 5 was a whole difference, a lot of difference. Can you imagine if you're just talking about compared to 2 to the 7th? You know, it makes a big deal. It makes a big deal. Matter of fact, 2 to the 7th is like 128. All right, those are all for that. So if you had any particular exponential function in a to the x, you could always make a table of values, you know, and you could plot your points. There's nothing wrong with that. But I want to share with you what the author wants you to see. That you could plot your points and no problem create your exponential growth. But in reality, you only needed 3 points that really helped you for the parent function. This is a parent function. As long as a is bigger than 1, that's a parent, okay? We always know that when we plug in a 0, you get a 1, because anything to the 0 power is 1. And then if you're plugging in a 1, you always know that a to the 1 is going to be itself, a. Now over here, if I'm plugging in a negative 1, it's probably right here. Yeah, that's about right. When you plug in a negative 1, a to the negative 1 always forces it to be 1 over a to the positive 1, always. So if you look at the table of values, there's an awful lot. And we're doing, if you're doing 2 to the x, look what happened at 0. Yes, sir, you got that. Look what happened at the 1. You got the base of a 2. That's what the base was. See, the base is a 2. 2 to the 1 is 2. If you plug in the negative 1, you always got the reciprocal of the base 2. You got the reciprocal of 2, which is 1/2. So you didn't really need these extra points. Not that I would stop you from producing them. Okay, now looking at this apparent function for exponential growth, you should realize that as you go to the left, we already talked about that the domain is all real numbers because you can keep going forever to the right and forever to the left. So I'm going to write domain as negative infinity to infinity. It always will be, always for an exponential growth. There's never any breaks, okay? Now the range for the parent, since this is the asymptote, that line here, y equals to 0, the x-axis, the range will never get lower than that. And I can't even put bracket. I cannot put bracket because it's never going to even be 0. It has to just be a parenthesis 0, and then it goes as high as the 7th heaven. So it just keeps going up. So as long as a is greater than 1, I'm going to say, and again, Jillian, you're reading the book. You can correct me if I'm putting in stuff the book doesn't have. But I'm looking at that that black function that I wrote here. I'm going to say it's increasing, and it is continuous. I think I can get away with it this time, because it really is continuous everywhere. It also is 1-to-1, so I'm pretty sure I can just say continuous on the domain of negative infinity to infinity. And then I already told you about this asymptote. On the parent function, it's the x-axis. Unless you shift the function up or down, the asymptote never changes. And I'm going to give you a little preview of some calculus that we talk about. If you're talking about this function, because he said, right here, he said, it's a horizontal asymptote as x approaches a negative infinity. So why don't I talk about what that means? That means the limit as x approaches a negative infinity of a to the x, as long as a is greater than 1. The limit means what's the y value that I'm approaching as I go to the left forever and ever. Left forever and ever and ever. What's the y value that I'm approaching that I never get to? It's the asymptote. It's 0. And if I go the other way, the limit as x approaches infinity, go on the other way of a to the x as long as a is greater than 1. As I go this way, what's the y value that I'm approaching? It's approaching infinity, which doesn't really exist. So when you start learning this stuff in calculus, that you start realizing you can put does not exist. You can say infinity or does not exist. Both are true. But infinity at least gives you a concept that it goes up forever. Okay? And what else I have to put here? Okay, the 3 points that he was wanting you to realize. That you get 1 over a when x is a -1, and when x is a 0, you get a 1. And when x is a 1, you actually get the a, whatever the a is. That looks like a 9. A. What if we switch the a to be between 0 and 1? You could make your table. Not a problem. You know, if I do 1 over 1/2 to the -3 power, what that means is both those numbers get the -3. So 1 to the -3 and 2 to the -3. But a 1 to the -3 is still a 1. And a 2 to the -3 means this has to go upstairs to become positive. It actually becomes 2 to the 3. So 2 to the 3 is 8. And which, if you look at his table, there it is, see? But that's a lot of work. You know, you can make your table. You could do the -2 now. You know, we can do the 1/2 to all to the -2. That becomes 1 over 2 to the -2, which is 1 over, well, not 1 over anymore because this has to be taken upstairs. That becomes just a 2 to the 2, 4. So there it is. But if you use that trick that we talked about, all I really need right now is 0, 1, and 1, 1, let's see, 1, 1/3. That's what that becomes. 1, 1/3. No, it's a half. Sorry, I was thinking it was a 2. It's a 1/2. A is a half, not a third. And then if I go to the -1, 1 over a, that might be hard for some of you. 1 over 1/2. Well, what is 1 over 1/2? You got to flip that bottom fraction and multiply. That's a 2. Well, that's why when he plugged in a 1, he got, or a -1, he got a 2. So you only really need these 3, and you can make a nice smooth curve, asymptotic to the x-axis, and then continuing up to heaven forever. So that's your parent now. So what he did is he switched it to an a between 0 and 1. The domain is still -infinity to infinity. The range did not change either. The lowest it can go is almost to the 0, never touching it though, so it's a parenthesis, still to infinity. And assuming that a is between 0 and 1, we know that the function now from left to right, it's getting smaller. So it's decreasing, and it's still continuous. And Jillian didn't correct me, so I'm thinking I'm okay to use that word on the entire domain of -infinity to infinity. Maybe Jillian has said, I have enough points extra now. I don't need to show off. The x-axis is still the horizontal asymptote. The limits are reversed now, though. The limit as I approach infinity now is 0, and the limit as I approach -infinity. See, right now he says, as I approach infinity, I'm approaching 0. That's the horizontal asymptote. If I approach -infinity, I'm going to infinity. And the line still passes through, that would be a -1 gets the 1 over a, and 0 gets the 1, and the 1 gets whatever a is. Short and sweet for those. Now, I've already talked about the increasing and decreasing bit, about the a's. Okay, so example 2. He wants us to graph. Okay, so there's my base. My a is a 1/3. That's between 0 and 1. So I know it's going to have to be a decay function. It's going to have to look like that. I know that. So I just drew it. And I know that at 0, it's going to be at the 1. And I know at 1, it's going to be a half. And I know at a negative 1, it's going to be a 3. Because of those secret magic points that we talked about. And the rest is magic, you know. I just know that as I continue getting closer to this asymptote, this is constantly getting lower and lower and lower because it's going to be a decreasing function. It's a decreasing function. And I know as I go to the left, it's going to rise and rise and rise forever. So I didn't have to think too much. Domain and range, same as before. Domain, negative infinity to infinity. The range, I want to be at 0, but I can't get there, to infinity. That's my range. It goes from 0 to infinity. Is he still graphing? Yeah, he's still graphing, but now we're going to translate them. We're going to move them around. Okay? So he's added a negative in front. This is not the same as this. This is bad news. This is really super bad news. This is not at all exponential growth or exponential decay. A has to be positive to be able to have, and A is positive because the A is not changing signs. There's a negative in front of the whole thing, which just means every answer is negative. That's all it means. Every answer that you put in here will be negative. When you get done, it'll always be negative. So before I do any work here, I'm going to talk about the parent, just 2 to the x. And for fun, I'm just going to graph it. 2 to the x looks like this, like my last answer. And I know that at negative 1, I was up here at 2 to the negative 1 was, was a half? Hold on here. 0 I know gives me a 1. And a 1, I drew it wrong. And nobody stopped me. I just saw what I did wrong. Why is that looking right? I drew a decay, guys. Why didn't you stop me? If 2 is, oh, why did I erase that one? If 2 is greater than 1, it's going to be a growth. Shame on you guys for not stopping me. There, that's better. The negative 1 does give me at the half. And the 1 does go up to 2. So here are my 3 important points on my parent. Can somebody tell me what happened on any function that I had when I put a negative in front? While you're thinking, I'm going to do this. What was the difference between x squared and y was a negative
over
x?
the x-axis.
What does it do there?
Flipped over the x-axis.
Is that you again, Julian?
Yeah.
Bingo, more points for you. It does. It reflects over the x-axis. So instead of me working too hard, let me just do this. Let me just reflect these points over the x-axis. The same distance apart, I drop it down. And it's still going to be approaching that axis, that horizontal asymptote, and now it's doing this. The domain is still negative infinity to infinity. Now, this was the parent. That was not the answer. I used it to graph the function we wanted. This was a negative 2 to the x. That's what I was graphing right here, a negative 2 to the x. That's this blue one. The range, though, the lowest it can go is now negative infinity. And it rises till I get to almost a 0. That one does change the range. Normally, I always say, oh, domain and range never changes. Well, it does if you flip it over the x-axis. All right, getting harder. Let's talk about the parent again. And I'm so lazy. I am so lazy, I just draw the same parent again. 0, 1, 1, 1/2, 1, 2. Same places, same points on the parent. But I need, and I hope there's somebody else paying attention. What happened to any function when you added a number to the x? What does the functions all do when you add to the x? Like y equals x squared versus y equals x squared plus 2.
Vertical
Wait,
translation.
hold on, I lied. Hold on. You're right, but I didn't mean to write that. Pretend I didn't say that. I meant this. I don't know who was going to answer that, but they were right. X plus 2 squared. Okay, there you go. That's what I wanted. Now, can you answer that again? What happens now?
It moves 2 to the left.
2 to the left. Well, this must also go left. How many? 3 left. So if you just want to cheat and not have to think too hard, watch this. 3 to the left. Remember when you add to x's, it means left. If you subtract from x, it moves to the right. So what I'm going to do is every point's going to move left 3. Here goes. 1, 2, 3. That point goes there. This point, okay, here goes. 1, 2, 3. That point goes here. This point, 1, 1, 2, 3. That point goes here. So those 3 red dots, still asymptotic to the x-axis. There it goes, there it goes, there it goes. And there is a pretty good rendition of what happens. Now, if you really want to be a good student, what you would do is actually, what are those ordered pairs? You know, that would be really nice if you could figure out what they are. But that just means whatever ordered pairs I had, my ordered pairs was -1, 1/2, 0, 1, 1, 2, is the new transform points was it was taking away how many? 3 from the x when I went left? Yeah. I went left 3. That meant x has changed. The y's didn't change. So if I take away 3, that's really a -4/2. That became a -3, 1. And that became 1 minus 3. 1 minus 3 is -2, right? -2, 2. So those are my new points. So if you were a good student, you would actually do some more thinking. But he just said, graph it, find the domain and range. Okay, my new domain and range. We're not talking about the parent. We're talking about that one. Domain. It's the same. Didn't change. Range. It's the same. It didn't change. Oh, no, it's 0 to infinity, right? That didn't change at all. Okay, the hardest of them. Look what's happening. 2 transformations. Right 2, down 1. Let me use my parent again. Always, it does, to me, it just, if I'm doing a fast sketch, it's nice to know what the parent looked like. And the parent looked like that. That's the parent. And yes, that was a 0, and that's a 1, and that's a 1, and that's a 2, and that's a -1, and that's a half. It's okay to look at these points and say, well, what are they going to do? It's a little more complicated. I got to go to the right 2 for this one. 1, 2. That takes it to a 3. And then I have to go down 1. So it goes down 1. That ordered pair becomes 3, 1. All right, let's do the 0. Right 2 becomes what? No, supposed to go, yeah, right 2. That's at a 2. Wait, 1, 2. And then I got to go down. I got to go down 1. So how far does it go if I go down 1? It goes to the 0. That point is 2, 0. How about this one here? Yeah, if I go to the right 2, 1, 2, then it has to go down 1. So if I go down to the x, that's a half, another half. There it is. That's now a 1 comma negative half. So I got my 3 new points, but I also want to share something with you. When you move up or down exponential, this is the parent function's horizontal asymptote. It also has to go down 1. So it goes down to a negative 1. So my new asymptote is down here. So now when I draw this, look what happens. Here it goes. And here it goes to the asymptote. There it is. Beautiful job. That may be the best job I've done all day. Okay, the domain. Did the domain change? No. The range did, though. Finally, the range changed. Well, it changed on the other problem, too. But this now, the lowest it can go is not 0. It's a negative 1. It'll never get there, though, but it wants to get there. And the highest it'll go will be heaven. Okay. Was there more on that page? I don't think so. Oh, yeah, there was. We are going to... Oh, why is that moving? We're going to graph. We're going to solve equations. Huh, that's a weird problem to start out with. Why is that doing that to me? Oh, because I'm not on the pen, that's why. Is there another problem? I didn't think that was the next problem, but I guess it is. I'm missing a problem. Your paper is missing a problem, I think. I don't know. Is this your next problem on your paper?
Yeah, it is.
Okay, I don't remember seeing that first thing. Okay, we need to solve this equation. Okay, and you got 1/3 to the x equals to 81. So the hard part is, oh, I know, I must have skipped this on the other class. I want to find the number x. Well, how can a fraction become a whole number? Think about it.
If it's negative,
Yeah, if it's negative. So now, if I want to make it negative, then that's 3 to some negative number. I think I can do that. So what must x be then? What negative number can this be, I should say? X has to be a negative number to make a negative and a negative. So what I want you to do is think of this. 3 to what power is 81?
4.
Yeah, I mean, you could simply think of that as, that has to be a 4.
Hmm.
So I would need x have to be a -4 then to get that to flip up like I did here to make it a 3, because then a -4 fits in there really well. Now sometimes somebody else might do this. Is there a way to write 81 with a base of 3, and that's 3 to the 4th, 3 times 3 times 3 times 3. So then we got the same base, So then x is 4. But if I wrote it the other way, 1/3, then I know I had to have the -4 to get that 3 up. That's a little more complicated than the next problem is. You're solving this one too. What we can do with this one, I think I will jump right to the fact that 8 can be written with 2's. I have 2x plus 4 in my exponent. This can still be a 2 to the third. And that 2 to the third has the x minus 6. But you should know that that's an exponent to an exponent. And the rule is an exponent to an exponent is you multiply these two together. So this becomes 2 to the x plus 4 equals 2 to the 3x minus 18. Now you may have said to yourself, why are you doing that? Because now look at, I got the same basis. A to the A equals A to the B as long as A equals to B, remember? So now you know that x plus 4 has to equal to 3x minus 18. Has to be true. And you can solve it now for this x and see which x works. So if I move the x over, that's a 2x. If I move the negative 18 over to a plus, or it was a negative 18, becomes a plus 18. I think I may have done this one wrong, another class. It should be plus 18, right? I think I did it wrong.
No, it's -18.
So it becomes a plus 18, right? So it's 22. I think I did it wrong in the other class. I think I subtracted 18. But nobody said anything. So x, I think x is 11.
Yes.
It's sad that I messed up on the solving an equation, a linear equation. And what's really more sad is nobody in 1B noticed. And that's real sad, so sad. Another one. That one looks real hard. But it really isn't. I'm not even going to worry about this 81. I'm going to look at how can I get x by itself. A power to a power could be used if I want to get rid of this power. How could I get rid of 4/8? What times 4/8 makes it go away? 4/3, I mean.
3/4.
3/4. But if you want to raise this to the 3/4, then I have to raise this to the 3/4. But that's fine because 12 over 12 is 1. That gives you x. And x 81 to the 3/4, just like I told you before, the 81 gets the 3, and that 4 means fourth root. And I know it's ugly, but it's not that bad because it's really fourth root of an 81 times a fourth root of an 81 times a fourth root of an 81. And we found the fourth root of 81 a few minutes ago. What times what times what times what was 81?
3.
3. So the answer is 3 times a 3 times a 3, which is 27. X is 27. So not too shabby. I mean, it's okay. All right. I made a mistake in the compound interest problem last period, and I caught it after I said that answer didn't make sense. I don't like his formula because he got me confused. I like this formula. Well, actually, oh, why am I hitting that for? I actually use the same formula. I say the amount of money you're going to have in the future is the principal that you start with, and I go 1 plus the interest rate. Yes, I do divide by n, the number of times that you're accumulating interest, how many times you compound. But I made a mistake that m should really be, I mean, m works, but you got to remember that that means n times t. This N down here times how many years you're going to keep it invested. I lost the NT. I only used the T and I messed up. So we're almost done. We're only going to have time to get one problem done. The problem is you're investing $1,000. It pays 4%. So this is my principal. This is my interest rate, which has to be written as a decimal, 0.04. And I'm compounding it quarterly. That means 4 times a year. So that means N is 4. And then he wants me to not take any money out for 10 years. So my amount of money will be $1,000, 1 plus 0.04 over 4 raised to the 4 times 10. I lost that 4 a while ago. So I'm going to clean that up for you. Then you're going to use the calculator. 1,000, 1 plus, that's a 0.01 raised to the 40. That's 1,000 times 1.01 raised to the 40. And if you key that in, tell me how much money we're going to have. Are we going to get rich? Can I retire in 4 years if I invest $1,000? Anybody? Answer? I think it was 1,400 and something.
1,488 point.
How many cents? 86?
Yeah.
Okay. Next question said, how much interest are you going to make? Well, that's easy. The amount in interest will be the amount you started, you make after 10 years minus the amount you started out with. So I had $1,000. No, I'm making 1488.86. I subtract 1,000. That's $488.86, I think, interest. And I'm out of time, and I will finish up the last bit of this. I'll have to submit another video up there. I'm going to post this one, and then I'll post the end of it later on today. All right? I am out of time. Get your My Math Lab done. Please don't leave unless you signed in chat, or else I will be marking you absent. Thanks for your help, Carla.
Bye, sir.
And Emilio, thank you too.
Bye, sir. Thank you.
Bye-bye, thank you.
Bye, sir.
Bye, Joseph. Hey, Joseph, Mr. Garcia
Yes.
was wondering if you were going to be wanting to do a meet from home on Saturday.
What time? Because I was taking like a test on that day.
There's I think it's at 10, the calculator, because you were doing his calculator a lot.